All right, listener, ready to dive deep. This time we're talking Linux kernel driver subsystems.
The code that makes your hardware actually, work.
It's complicated stuff,
Yeah.
but we'll make it fun.
Yeah.
We've got mastering Linux device driver development to guide us.
Yeah, think of it like this. You've got all this amazing hardware in your computer, but it's like they all speak different languages.
Yeah.
Drivers are the interpreters, making sure they all work together.
Okay, so let's jump right in. Kernel locking. The book uses some interesting examples here.
Yeah.
Imagine a bunch of programs all trying to use your printer at the same time.
Oh, total chaos.
Disaster, right?
Yeah, pages, half printed, error message everywhere. So the kernel uses these things, locking mechanisms like spin locks and mutexes.
Okay, so what's the difference?
A spin lock, imagine you're constantly checking if the line is open, like waiting for your turn.
Got it.
But if you know it's going to be a long wait, you might as well, I don't know, grab a coffee, come back later.
Right.
That's more like a mutex.
So spin lock for quick things, mutex when you gotta wait.
Exactly.
What about tasks that don't need to be done right away? I mean, if I'm downloading a huge file, everything else can't just stop, right?
No, definitely not. And that's where work deferring comes in. Instead of halting everything, the kernel's got this system for scheduling tasks. Let's say a driver needs to write data to your hard drive.
Yeah.
It can use a work queue to schedule that for later, so the CPU can focus on more urgent stuff.
Ah, so it's like a to-do list.
Basically, yeah. You've got softbooks, task lists, work queues, all these things working together to keep things running smoothly. Prioritizing, managing resources,
Okay, now something that's always fascinated me, interrupts. How does my computer know I just hit a key on the keyboard?
Okay, picture this. You're the CPU, busy, doing calculations, and suddenly the keyboard sends this interrupt signal.
Like, hey, pay attention.
Right, like a digital tap on the shoulder. New keystroke here. CPU pauses, handles the interrupt, then goes back to what it was doing.
Wow, so it's like a constant stream of interruptions, but the kernel handles it all.
Yeah, it's amazing, isn't it?
Hmm.
Speaking of managing things, let's talk about some of those driver architectures.
Okay, the frameworks, right.
Yeah, like the blueprints for how drivers are structured.
Cool.
We'll start with the RegMap API.
RigMap, what's that all about?
Think of it like a translator for talking to hardware.
Okay.
A lot of devices have these things called registers, little storage locations that control how they behave.
Right.
RegMap API provides a standardized way to access and change those registers, makes the code much cleaner.
So instead of writing custom code for every single register, you can just use this API.
Yeah, simplifies things a lot.
Yeah.
Now, imagine a chip that does a bunch of different things, like a Swiss Army knife of hardware.
Ah, that's where the NFT subsystem comes in, right?
You got it. Multifunction device, we can manage all those different functions with one driver.
Efficiency. I like it. But what if those different devices need to share resources?
Good question. That's where the Syscon API comes in.
Right.
It helps manage those shared resources gracefully.
So it's like a traffic cop.
Exactly, making sure everything flows smoothly, no conflicts.
Okay, this is starting to make sense. Now, the clock framework. It's not just about telling time, right?
Definitely not. This one's about managing the clock signals that synchronize your hardware.
Okay, so it's important.
Imagine an orchestra where all the instruments are playing out of sync. It would be a mess. The clock framework keeps everything in rhythm.
Wow, the conductor of the hardware orchestra.
Exactly. And speaking of orchestrating, what about audio?
Oh yeah, that's got to be complicated.
We've got ALSA SoC for that, Advanced Linux Sound Architecture for System on Chip. It handles everything, audio codecs, digital interfaces, the whole shebang.
So when I'm listening to music, it's ALSA, so making sure it sounds good.
You got it.
All right, so we've got audio covered. What about video?
For that, we've got V4L2, Video for Linux 2, manages all your video capture devices, webcams, high-end cameras, everything.
Lights, camera, action.
Handles the data streaming, camera settings, all that.
Okay, audio, video. What about all the other stuff connected to my computer? Graphics card, network adapter, hard drive, all that.
You're talking about the backbone, PCI, Peripheral Component Interconnect. And each PCI device needs its own driver.
PCI drivers. What makes them special?
They handle the communication between the PCI devices and the CPU, make sure data flows smoothly and reliably.
Super important.
Oh yeah, mission critical. They manage everything from device identification to memory mapping, interrupt handling, the works.
Wow, that's a lot. And I bet if something goes wrong with a PCI driver, things can get messy.
You're telling me, debugging PCI drivers can be a real headache. Luckily, the kernel's got some tools to help us out.
Okay, so let's talk debugging tools. I'm ready to get my hands dirty.
All right, let's start with the bread and butter, the print function.
Print. Is that just a fancy way of saying print?
Pretty much, yeah. But it's specifically for the kernel environment. Lets you add messages to the kernel log. Really helpful for understanding what your code is doing.
So like leaving notes for yourself.
Exactly. You can check variable values, spot errors, see how your code is flowing. And the cool thing is you can categorize your messages with different log levels.
Oh, so you can control how much information you're getting.
Exactly. From critical errors down to like really detailed debug stuff.
Okay, so print is great for the basics, but what if you need something more powerful?
Then we bring out the big guns. Theft trace.
Theft trace, that sounds intense.
It's a function call tracer. Gives you a detailed view of how your code's executing.
Okay, so if print is like leaving notes, is ftrace like recording a video of your code?
Perfect analogy. You can see the exact sequence of function calls, the arguments passed, even the time spent in each function.
Wow, that's like having X-ray vision into your code.
It is super helpful for finding performance bottlenecks and, those weird, hard-to-find bugs.
Okay, so print for basic debugging, ftrace for when you need to go deeper. What about when things go really wrong, like system crash wrong?
Then we need to analyze those kernel oops messages.
Kernel oops? Is that like the Linux version of the blue screen of death?
Kind of, yeah. It indicates a serious error, but doesn't always mean a full crash. The key is to analyze that oops message. It's packed with clues about what went wrong.
Like a crime scene investigation.
Exactly. You got to examine the evidence. Type of error, location in the code, even the state of the CPU.
Okay, so print, ftrace, and kernel, oops messages, our debugging toolkit.
That's the starting lineup. But remember, debugging is as much an art as it is a science,
Right, takes practice and patience. Okay, so we've covered a lot of ground.
Barely scratched the surface.
I know, right? What other adventures await us in the land of drivers?
Well, we've only touched on a few of the many driver architectures out there. Each one has its own challenges, its own solutions.
I'm ready for more.
Let's delve into some of the more specialized subsystems, starting with NVM, non-volatile memory.
NVM, that's like what's used in SSDs.
Yeah, SSDs are one type, but the NVM framework in the kernel is more about managing those smaller chunks of non-volatile memory, often embedded within other devices.
Okay, so memory that keeps its data even when the power's off.
Right. Could be boot settings, calibration data, error logs, all sorts of things. The long-term memory of your hardware, if you will.
Interesting. So how does the framework help drivers manage that?
Provides a standardized way to access and change those NVM regions. Abstracts away all the complexities of different hardware. Makes it much easier for developers.
Common language for talking to NVM.
Exactly. Now let's talk about a component that can save you a lot of headaches. The watchdog timer.
Watchdog timer. Sounds a little intimidating.
Imagine this. Your system's running fine, then suddenly a process goes haywire, everything freezes. The watchdog timer is like a safety net.
Okay.
It detects when the system's unresponsive and forces a reboot.
So it's like a reset button.
You got it. You can even configure it to trigger after a specific amount of time. Super important for system stability, especially in embedded systems.
So if you're working with a system that's prone to crashing, you can set the timer to be shorter.
Exactly. Get things back on track faster. It's a crucial part of making sure those critical systems stay up and running.
Wow, we've covered a lot, but it feels like we've only just begun to explore this world.
Oh, we've got a long way to go.
I can't wait.
But with every step, we're getting a clearer picture of how these amazing pieces of code work, how they connect software and hardware.
It's like we're peeking behind the curtain, seeing how the magic happens.
Exactly. And the more we learn, the more we appreciate just how clever and complex the Linux kernel really is. So you're itching to write your own driver, huh? Well, before you unleash your code on the world, you'll want to test it thoroughly. And that's where our deep dive into debugging gets even more interesting.
Debugging challenges? Bring it on. I'm ready to solve some kernel mysteries.
All right. Remember that print function.
Our trusty print.
It's not just for basic debugging, you know? Use it strategically. It can be really powerful for those tricky bugs.
Okay, so more than just sprinkling print statements everywhere.
Yeah, much more. Think of it like this. You're hunting a bug that only shows up under very specific conditions.
Right.
You can use conditional print statements.
Oh, I see.
They only output messages when those conditions are met. You create a targeted log, zero in on the problem.
So it's like setting traps to catch the bug red-handed.
Exactly.
Okay.
You can even use print to track how your code's executing, make sure functions are being called in the right order with the right arguments, all that.
Smart.
Yeah.
So print for targeted debugging. What about when we need to see the bigger picture, like how our code is performing overall?
That's when we turn to ftrace, our function call tracer. Remember those high-definition videos of your code running?
Yeah.
Well, ftrace can capture even more detail, timestamps for each function call.
Oh, wow.
We can analyze performance bottlenecks really precisely.
So you can see exactly how long each function is taking.
Exactly. And you can filter it to only trace specific functions or even kernel threads. See how your driver is interacting with the rest of the kernel. Powerful stuff.
It's like having superpowers. You can see everything that's going on.
Pretty much. And don't forget about those kernel oops messages.
Right, the kernel's way of saying, whoops, something went wrong.
They might seem a little cryptic at first, but they're packed with clues. It's like deciphering a secret code. First, you got to figure out what kind of error it is, null pointer, memory violation, what have you.
Okay.
Then you look for where it happened in the code. The oops message will often tell you the function, even the line number. Then you look at the state of the CPU, the registers, and that can give you even more information.
So it's like a treasure map leading you to the source of the problem.
Exactly. All right, so we've got our prink for logging, ftrace for performance, and those oops messages for crash analysis. That's our debugging toolkit.
The essentials.
Exactly. But remember, debugging, it's not just about the tools. It's about understanding the system. It takes patience, a willingness to experiment. Speaking of experimenting, let's shift gears a bit. Talk about some specific types of drivers.
Yeah, okay. Let's dive into how drivers handle different kinds of hardware.
Perfect. Let's start with something close to home input devices. Every time you move your mouse, click a button, tap your touchscreen, that's an input driver at work.
So it's not just keyboards and mice these days, is it?
Oh no, not at all. Game controllers, joysticks, graphics tablets, even the sensors in your phone. It's a whole world of input devices out there.
So the drivers have to handle all sorts of different devices and protocols.
Exactly. And they need to make sure those interactions are smooth, responsive. They work closely with the kernel's input subsystem, event handling, device mapping, filtering, all that good stuff.
Wow, sounds complicated. Okay, so what about output devices? Things like displays and printers.
Another set of challenges. Display drivers need to manage frame buffers, handle different resolutions and refresh rates, optimize for smooth video, all that. Printer drivers, well, they deal with page sizes, color models, printer-specific commands, a whole other beast.
It's amazing how much work goes into making all this stuff just work seamlessly.
It is. It's a testament to the developers who write this code. And then you've got networking, which is a whole other world.
Networking, yeah. That's got to be complex.
Oh, it is. Network drivers handle everything from those Ethernet packets to wireless signals, making sure your computer can actually talk to the outside world.
So we've got input drivers, output drivers, network drivers. What else?
Well, we've talked about storage drivers for your hard drives and SSDs, but you've also got drivers for sound cards, graphics cards, USB devices, even random number generators.
Wait, random number generators need drivers?
You'd be surprised. They're used in cryptography, simulations, even games. The driver interfaces with the hardware that generates the random numbers.
Learn something new every day. It seems like everything in a computer needs a driver.
You got it. Drivers are the unsung heroes, working behind the scenes to make our digital lives possible. But let's move on from specific types of drivers and talk about some core mechanisms that all drivers use. How about memory management?
Okay, memory management. I know that's important for operating systems in general, but what's it got to do with drivers?
Well, drivers often need to allocate and manage memory for different purposes. A network driver might need to allocate buffers for data packets. A graphics driver needs memory for frame buffers, and so on.
So they're all sharing the same memory pool, so to
Exactly. And they have to play by the rules, use the kernel's memory management APIs to make sure everything's done properly.
What happens if a driver tries to access memory it shouldn't?
Oh, that's bad news. Memory access violations can cause all sorts of problems. System crashes, data corruption, you name it. That's why the kernel has all these safeguards in place, memory protection, address space isolation.
Right, to keep things running smoothly. Speaking of running smoothly, what about concurrency?
Ah, yes. Concurrency. Modern systems are all about doing multiple things at the same time.
Multitasking.
Right. And drivers need to be able to handle that gracefully. Imagine you're streaming a video, downloading a file, editing a document, all at the same time. Each of those tasks might involve different drivers.
And they all need to work together without stepping on each other's toes.
Exactly. Drivers need to be designed carefully to avoid race conditions.
Race conditions.
It's when the outcome of an operation depends on the timing of multiple events.
So it's like a race between different parts of the code, and the result is unpredictable.
Exactly. And that can lead to some really nasty bugs. That's why drivers use things like spin locks, mutexes, semaphores, all these synchronization mechanisms to coordinate access to shared resources.
This is getting pretty complex. No wonder driver development is considered such a specialized area.
It's definitely challenging, but also incredibly rewarding. When you understand how to write drivers, you really understand how the operating system works at a deep level.
Okay, so we've gone from debugging techniques to different types of drivers. Now we're talking about memory management and concurrency.
Yeah.
It's like peeling back the layers of the onion, revealing more and more complexity.
And we're not done yet. Let's talk about something that's essential for any driver that talks directly to hardware. I/O, input-output.
I/O sounds pretty basic,
Uh,
but I'm guessing it's more complicated than it sounds.
You bet. I/O operations can get pretty involved. Drivers need to deal with different addressing schemes, handle interrupts from devices, manage DMA, all that fun stuff.
DMA, right. We talked about that with PCI, didn't we?
We did. DMA lets devices transfer data directly to and from memory without bothering the CPU.
So it's like a high-speed lane for data, bypassing the CPU.
Perfect analogy. But drivers need to manage those DMA transfers carefully. Set up memory mappings, configure the controller, make sure everything's transferred correctly. It's a lot to juggle.
I'm starting to see how all these pieces fit together. Drivers handling memory, concurrency, I/O, all working together to create that bridge between software and hardware.
Exactly. And each of these areas has its own set of challenges and best practices. But with a solid understanding of the core concepts, you're well on your way to mastering driver development.
All right, so we've covered a lot today. Different types of drivers, memory management, concurrency, I/O. We even sharpened our debugging skills. What's next on our driver development journey?
Let's shift gears a little bit and talk about some tools and techniques that developers use to analyze and optimize their code. Because writing a driver is one thing, making sure it's efficient and reliable, that's another challenge altogether.
Okay, let's level up our skills. What kind of tools are we talking about?
Well, let's start with something called static analysis. This involves analyzing your code without actually running it. There are tools that can find potential bugs, coding style violations, even security vulnerabilities.
So it's like a code review, but before you even compile.
Exactly. Static analysis can save you a ton of time and headaches by catching those errors early. And then there's dynamic analysis.
Dynamic analysis.
This is about monitoring your code as it's running. You collect data on performance, memory usage, all those key metrics.
So it's like having a dashboard for your driver.
Precisely. You can spot bottlenecks, memory leaks, other issues that might not be obvious just by looking at the code. And then there's unit testing.
Unit testing, yeah. I've heard of that, but not sure how it applies to drivers.
Okay, imagine you've written a function that reads data from a device.
Okay.
With unit testing, you write a separate test function that calls that read function with different inputs, different scenarios, make sure it returns the expected output. You're basically setting up mini experiments to verify that each part of your code is working correctly.
So you're testing it in isolation, piece by piece.
Exactly. And the best part is you can automate those tests. Run them every time you change the code, make sure you haven't broken anything.
Keeps everything working smoothly. What about when you really need to get down to the nitty-gritty? Understand exactly how your driver is talking to the hardware.
For that, we have kernel debugging tools, things like KGDB and KDB.
Okay, hardcore debugging mode.
Pretty much. You can step through your code line by line, look at the memory, really get into the guts of the system.
Sounds intense.
It is, but it's a valuable skill, especially when you're working with hardware at a low level.
All right, so we've got static analysis, dynamic analysis, unit testing, and kernel debugging. A whole arsenal of tools for driver development.
Those are the big ones. But remember, the best tool is your own understanding of the system, your intuition, your ability to reason about how things work.
So it's not just about blindly using tools, it's about understanding the bigger picture.
Exactly. And the more you learn about the Linux kernel, the more you'll appreciate its elegance, its power.
Okay, we're back for the final part of our deep dive into Linux kernel driver subsystems. We've talked about how drivers work, how to debug them, all sorts of things. What else is there to explore?
Well, we've focused a lot on how drivers talk to the hardware, how they interact with the kernel. But there's another important piece, how they interact with user space.
Right, the actual users and applications.
Exactly. After all, the whole point of a driver is to make the hardware accessible to users.
Hmm.
So how do they bridge that gap between kernel space, where the drivers live, and user space, where our applications are running?
Yeah, how does that work?
There are a few ways. One common approach is system
The
calls.
system calls, okay.
User space applications can make system calls to ask the kernel for services, and drivers can expose their functionality through these calls.
So it's like a request line from user space to kernel space.
Yeah, think of it like a phone line. The application dials up the kernel and says, hey, I need to use this device, and the driver picks up the phone.
Makes sense.
Another important mechanism is device files. These special files in the file system, they represent physical or virtual devices.
Device files, right, I remember those. They're in the dev directory, right.
Exactly. Things like devsda for your hard drive, devd-usb-0 for a USB serial port. Drivers use these device files to provide a user-friendly interface to their hardware.
So the application can just treat the hardware like a file.
Pretty much, yeah. They can open it, read from it, write to it, just like any other file. But the kernel intercepts those operations and sends them to the driver.
Clever. So system calls and device files. What else?
There's also IOCTL,
Well,
input-output control.
okay.
It's a special system call that lets applications send custom commands to drivers and get back driver-specific data.
So if an application needs to do something really specific with a device, it can use IOCTL.
Exactly. Gives developers a lot of flexibility.
Hmm.
But it can also be a bit risky if you're not careful. Security vulnerabilities, system instability, that kind of thing.
Right, so it's a powerful tool, but you got to use it responsibly.
Absolutely. And let's not forget about power management.
Oh, right. Power management's a big deal these days, especially with mobile devices.
Exactly. Drivers play a crucial role in making sure devices use power efficiently.
So how do they do that?
They can register with the kernel's power management subsystem, tell it about the device's different power states, how to transition between them. Then the kernel can automatically power down the device when it's not being used and power it back up when it's needed.
So it's like putting the device to sleep and waking it up.
Yeah, pretty much. Of course, some devices need to stay active even when the system's idle.
Right, like a network card that needs to listen for incoming data.
Exactly. Drivers need to be designed to handle those cases. Things like wake on LAN, where the device can wake up the system if it receives a specific network packet.
So it's like a little alarm clock for the system.
You got it. Okay, so we've talked about how drivers communicate with user space, how they manage power, but there's so much more to explore. The world of drivers is vast.
It is, isn't it? It barely scratched the surface.
There are all these specialized driver architectures and frameworks, each one tailored to specific types of devices. We talked about ALSA SoC for audio, V4L2 for video, but there's also IIO for industrial I/O, MMC for memory cards, DRM for graphics, and so on.
It's amazing how many different types of drivers there are, and each one has its own unique challenges. It's like the world of drivers is as diverse as the hardware itself.
Exactly. And that's what makes it so fascinating. There's always something new to learn, a new challenge to tackle. And as technology keeps advancing, the world of drivers will only become more complex and exciting.
Well, I think that brings us to the end of our deep dive. What an incredible journey it's been. We've explored so much, from the basic concepts to those complex interactions between the kernel, drivers, hardware, and user space.
It's been quite a ride. But remember, this is just the beginning. The world of Linux kernel driver development is constantly evolving. There's always more to learn, more to discover.
I feel like I've gained a whole new appreciation for how crucial drivers are. They're the unsung heroes that make our computers and devices work.
And the best part is, all of this knowledge is freely available thanks to the open source nature of Linux. Anyone can explore it, learn from it, even contribute to it.
So to all our listeners out there, if you're feeling inspired, why not dive into the world of drivers yourselves? You might just create the next game-changing driver that revolutionizes how we interact with technology. Until next time, happy hacking.